Section 1 of Radioactive Substances. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in July 2010. Radioactive Substances by Madame Sklodowska-Curie. Thesis presented to the Faculté des Sciences de Paris. Introduction. The object of the present work is the publication of researches which I have been carrying on for more than 4 years on radioactive bodies. I began these researches by a study of the phosphorescence of uranium discovered by M. Becquerel. The results to which I was led by this work promised to afford so interesting a field that M. Curie put aside the work on which he was engaged and joined me, our object being the extraction of new radioactive substances and the further study of their properties. Since the commencement of our research, we thought it well to hand over specimens of the substances discovered and prepared by ourselves to certain physicists, in the first place to M. Becquerel, to whom is due the discovery of the uranium rays. In this way we ourselves facilitated the research by others besides ourselves on the new radioactive bodies. At the termination of our first publications, M. Giesel, in Germany, also began to prepare these substances, and passed on specimens of them to several German scientists. Finally, these substances were placed on sale in France and Germany, and the subject growing in importance gave rise to a scientific movement, such that numerous memoirs have appeared and are constantly appearing on radioactive bodies, principally abroad. The results of the various French and foreign researches are necessarily confused, as is the case with all new subjects in course of investigation, the aspect of the question becoming modified from day to day. From the chemical point of view, however, one point is definitely established, that is, the existence of a new element, strongly radioactive, that is, radium. The preparation of the pure chloride of radium and the determination of the atomic weight of radium form the chief part of my own work. Whilst this work adds to the elements actually known with certainty a new element with very curious properties, a new method of chemical research is at the same time established and justified. This method, based on the consideration of radioactivity as an atomic property of matter, is just that which enabled M. Curie and myself to discover the existence of radium. If, from the chemical point of view, the question that we undertook primarily may be looked upon as solved, the study of the physical properties of the radioactive bodies is in full evolution. Certain important points have been established, but a large number of the conclusions are still of a provisional character. This is not surprising when we consider the complexity of the phenomena due to radioactivity and the differences existing between the various radioactive substances. The researches of physicists on these substances constantly meet and overlap. Whilst endeavoring to keep strictly to the limits of this work and to publish my individual research only, I have been obliged at the same time to mention results of other researches, the knowledge of which is indispensable. I desired, moreover, to make this work an inclusive survey of the actual position of the question. I indicate at the end the particular questions with which I am specially concerned, and those which I investigated in conjunction with M. Curie. I carried on the work in the laboratories of the School of Physics and Chemistry in Paris, with the permission of Schützenberger, late director of the school, and M. Laut, actual director. I take this opportunity of expressing my gratitude for the kind hospitality received in this school. Historical. The discovery of the phenomena of radioactivity is connected with researches followed since the discovery of the Roentgen rays upon the photographic effects of phosphorescent and fluorescent substances. The first tubes for producing Röntgen rays were without the metallic anticathode. The source of the Röntgen rays was the glass surface impinged upon by the cathode rays. This surface was at the same time actively fluorescent. The question then was whether the emission of Röntgen rays necessarily accompanied the production of fluorescence, whatever might be the cause of the latter. This idea was first enunciated by M. Henri Poincaré. Shortly afterwards, M. Henry announced that he had obtained photographic impressions through black paper by means of phosphorescent zinc sulphide. M. Niewenglowski obtained the same phenomenon with calcium sulphide exposed to the light. Finally, M. Trost obtained strong photographic impressions with zinc sulphide artificially phosphorescent acting across black paper and thick cardboard. The experiences just cited have not been reproduced, in spite of numerous attempts to this end. It cannot therefore be considered as proved that zinc sulphide and calcium sulphide are capable of emitting, under the action of light, invisible rays which traverse black paper and act on photographic plates. M. Becquerel has made similar experiments on the salts of uranium, some of which are fluorescent. He obtained photographic impressions through black paper with the double sulphate of uranium and potassium. M. Becquerel at first believed that this salt, which is fluorescent, behaved like the sulphides of zinc and calcium in the experiments of Messrs. Henry, Niewenglowski, and Trost. But the conclusion of his experiments showed that the phenomenon observed was in no way related to the fluorescence. It is not necessary that the salt should be fluorescent. Further, uranium and all its compounds, fluorescent or not, act in the same manner, and metallic uranium is the most active. M. Becquerel finally found that by placing uranium compounds in complete darkness, they continue acting on photographic plates through black paper for years. M. Becquerel allows that uranium and its compounds emit peculiar rays, uranium rays. He proved that these rays can penetrate thin metallic screens, and that they discharge electrified bodies. He also made experiments from which he concluded that uranium rays undergo reflection, refraction, and polarization. The work of other physicists, Elster and Geitel, Lord Kelvin, Schmidt, Rutherford, Beatty, and Smoluchowski, confirms and extends the results of the researches of M. Becquerel, with the exception of those relating to the reflection, refraction, and polarization of uranium rays, which in this respect behave like Röntgen rays, as has been recognized first by Mr. Rutherford, and then by M. Becquerel himself. End of section 1. Section 2 of Radioactive Substances. This LibriVox recording is in the public domain. Read by Availle in July 2010. Radioactive Substances by Marie Curie. Chapter 1. Radioactivity of Uranium and Thorium. Radioactive Minerals. Becquerel rays. The uranium rays discovered by M. Becquerel act upon photographic plates screened from the light. They can penetrate all solid, liquid, and gaseous substances, provided that the thickness is sufficiently reduced in passing through a gas, they cause it to become a feeble conductor of electricity. These properties of the uranium compounds are not due to any known cause. The radiation seems to be spontaneous. It loses nothing in intensity, even on keeping the compounds in complete darkness for several years. Hence, there is no question of the phosphorescence being specially produced by light. The spontaneity and persistence of the uranium radiation appear as a quite unique physical phenomenon. M. Becquerel kept a piece of uranium for several years in the dark, and he has affirmed that at the end of this time the action upon a photographic plate had not sensibly altered. Messrs. Elster and Geitel made a similar experiment, and also found the action to remain constant. I measured the intensity of radiation of uranium by the effect of this radiation on the conductivity of air. The method of measurement will be explained later. I also obtained figures which prove the persistence of radiation within the limits of accuracy of the experiments. For these measurements a metallic plate was used, covered with a layer of powdered uranium. This plate was not otherwise kept in the dark, this precaution, according to the experimenters already quoted, being of no importance. The number of measurements taken with this plate is very great, and they actually extend over a period of 5 years. Some researches were conducted to discover whether other substances were capable of acting similarly to the uranium compounds. M. Schmidt was the first to publish that thorium and its compounds possess exactly the same property. A similar research made contemporaneously gave me the same result. I published this, not knowing at the time of Schmidt's publication. We shall say that uranium, thorium, and their compounds emit Becquerel rays. I have called radioactive those substances which generate emissions of this nature. This name has since been adopted generally. In their photographic and electric effects, the Becquerel rays approximate to the Roentgen rays. They also, like the latter, possess the faculty of penetrating all matter. But their capacity for penetration is very different. The rays of uranium and of thorium are arrested by some millimeters of solid matter, and cannot traverse in air a distance greater than a few centimeters. This at least is the case for the greater part of the radiation. The researches of different physicists, and primarily of Mr. Rutherford, have shown that the Becquerel rays undergo neither regular reflection, nor refraction, nor polarization. The feeble penetrating power of uranium and thorium rays would point to their similarity to the secondary rays produced by the Roentgen rays, and which have been investigated by M. Sagnac, rather than to the Roentgen rays themselves. For the rest, the Becquerel rays might be classified as cathode rays propagated in the air. It is now known that these different analogies are all legitimate. Measurement of the intensity of radiation. The method employed consists in measuring the conductivity acquired by air under the action of radioactive bodies. This method possesses the advantage of being rapid and of furnishing figures which are comparable. The apparatus employed by me for the purpose consists essentially of a plate condenser, AB in Fig. 1. The active body, finely powdered, is spread over the plate B, making the air between the plates a conductor. In order to measure the conductivity, the plate B is raised to a high potential by connecting it with one pole of a battery of small accumulators, P, of which the other pole is connected to earth. The plate A being maintained at the potential of the earth by the connection CD, an electric current is set up between the two plates. The potential of plate A is recorded by an electrometer, E. If the earth connection be broken at C, the plate A becomes charged, and this charge causes a deflection of the electrometer. The velocity of the deflection is proportional to the intensity of the current, and serves to measure the latter. But a preferable method of measurement is that of compensating the charge on plate A, so as to cause no deflection of the electrometer. The charges in question are extremely weak. They may be compensated by means of a quartz electric balance, Q, one sheath of which is connected to plate A and the other to earth. The quartz lamina is subjected to a known tension, produced by placing weights in a plate π. The tension is produced progressively, and has the effect of generating progressively a known quantity of electricity during the time observed. The operation can be so regulated that, at each instant, there is compensation between the quantity of electricity that traverses the condenser and that of the opposite kind furnished by the quartz. In this way, the quantity of electricity passing through the condenser for a given time, that is, the intensity of the current, can be measured in absolute units. The measurement is independent of the sensitiveness of the electrometer. In carrying out a certain number of measurements of this kind, it is seen that radioactivity is a phenomenon capable of being measured with a certain accuracy. It varies little with temperature, it is scarcely affected by variations in the temperature of the surroundings, it is not influenced by incandescence of the active substance. The intensity of the current which traverses the condenser increases with the surface of the plates. For a given condenser and a given substance, the current increases with the difference of potential between the plates, with the pressure of the gas which fills the condenser, and with the distance of the plates, provided this distance be not too great in comparison with the diameter. In every case, for great differences of potential, the current attains a limiting value which is practically constant. This is the current of saturation, or limiting current. Similarly, for a certain sufficiently great distance between the plates, the current hardly varies any longer with the distance. It is the current obtained under these conditions that was taken as the measure of radioactivity in my researches, the condenser being placed in air at atmospheric pressure. I append curves which represent the intensity of the current as a function of the field established between the plates, for two different plate distances. Plate B was covered with a thin layer of powdered metallic uranium. Plate A, connected with the electrometer, was provided with a guard ring. Figure 2 shows that the intensity of the current becomes constant for high potential differences between the plates. Figure 3 represents the same curves on another scale, and comprehends only relative results for small differences of potential. At the origin, the curve is rectilinear. The ratio of the intensity of the current to the difference of potential is constant for weak forces, and represents the initial conduction between the plates. Two important characteristic constants of the observed phenomenon are therefore to be recognized. 1. The initial conduction for small differences of potential. 2. The limiting current for great potential differences. The limiting current has been adopted as the measure of the radioactivity. Besides the difference of potential established between the two plates, there exists between them an electromotive force of contact, and these two sources of current combine their effects. For this reason, the absolute value of the intensity of the current changes with the sign of the external difference of potential. In every case, for considerable potential differences, the effect of the electromotive force of contact is negligible, and the intensity of the current is therefore the same whatever be the direction of the field between the plates. The investigation of the conductivity of air and other gases subjected to the action of Becquerel rays has been undertaken by several physicists. A very complete research upon the subject has been published by Mr. Rutherford. The laws of the conductivity produced in gases by the Becquerel rays are the same as those found for the Roentgen rays. The mechanics of the phenomenon appear to be the same in both cases. The theory of ionization of the gases by the action of the Roentgen or Becquerel rays agrees well with the observed facts. This theory will not be put forward here. I will merely record the results to which they point. Firstly, the number of ions produced per second in the gas is considered proportional to the energy of radiation absorbed by the gas. Secondly, In order to obtain the limiting current relatively to a given radiation, it is necessary, on the one hand, to cause complete absorption of this radiation by the gas by employing a sufficient mass of it. On the other hand, it is necessary for the production of the current to use all the ions generated by establishing an electric field of such strength that the number of the ions which recombine may be a negligible fraction of the total number of ions produced in the same time, most of which are carried by the current to the electrodes. The strength of the electric field necessary to give this result is proportional to the amount of ionization. According to the recent researches of Mr. Townsend, the phenomenon is more complex when the pressure of the gas is low. At first, the current appears to approach to a constant limiting value with increasing difference of potential, but after a certain point has been reached, the current begins again to increase with the field, and with very great rapidity. Mr. Townsend ascribes this increase to a new ionization produced by the ions themselves when under the action of the electric field they acquire a velocity such that a molecule of gas encountering one of them becomes broken down into its constituent ions. A strong electric field and a low pressure are favourable to the production of this ionization by ions already present, and, as soon as the action is set up, the intensity of the current increases uniformly with the field between the plates. The limiting current could, therefore, only be obtained under conditions of ionization of which the intensity does not exceed a certain value, and in such a manner that saturation corresponds to fields in which, from multiplicity of ions, ionization can no longer take place. This condition has occurred in my experiments. The order of magnitude of the saturation currents obtained with uranium compounds is 10 to the power of 11 amperes for a condenser in which the plates have a diameter of 8 cm and are at a distance of 3 cm. Thorium compounds give rise to currents of the same order of magnitude, and the activity of the oxides of uranium and thorium is very similar. Radioactivity of the compounds of uranium and thorium. The following are the figures I obtained with different uranium compounds. I have represented the intensity of the current in ampere by the letter I. Metallic uranium containing a little carbon, intensity of the current 2.3 × 10 to the 11 ampere. Black oxide of uranium U2O5, intensity of the current 2.6 × 10 to the 11 ampere. Green oxide of uranium U3O4, intensity of the current 1.8 × 10 to the 11 ampere. Hydrated uranic acid, intensity of the current 0.6 × 10 to the 11 ampere. Uranate of sodium, intensity of the current 1.2 × 10 to the 11 ampere. Uranate of potassium, intensity of the current 1.2 × 10 to the 11 ampere. Uranate of ammonium, intensity of the current 1.3 × 10 to the 11 ampere. Uranium sulfate, intensity of the current 0.7 × 10 to the 11 ampere. Sulfate of uranium and potassium, intensity of the current 0.7 × 10 to the 11 ampere. Nitrate of uranium, intensity of the current 0.7 × 10 to the 11 ampere. Phosphate of copper and uranium, intensity of the current 0.9 × 10 to the 11 ampere. Oxysulfide of uranium, intensity of the current 1.2 × 10 to the 11 ampere. The thickness of the layer of the uranium compound used has little effect, provided that the layer is uniform. The following illustrate this point. Uranium oxide, thickness of layer 0.5 mm, intensity of the current 2.7 × 10^11 ampere. Uranium oxide, thickness of layer 3 mm, intensity of the current 3 × 10^11 ampere. Ammonium uranate, thickness of layer 0.5 mm, intensity of the current 1.3 × 10^11 ampere. Ammonium uranate, thickness of layer 3 mm, intensity of the current 1.4 × 10^11 ampere. It may be concluded from this that the absorption of uranium rays by the substance which generates them is very great, since the rays proceeding from deep layers produce no significant effect. The figures I obtained with thorium compounds enable me to state, firstly, that the thickness of the layer used has considerable effect, especially in the case of the oxide. Secondly, that the action is only regular if a sufficiently thin layer is used, for example 0.25 mm. On the contrary, when a thick layer of the substance is used, 6 mm, the figures obtained vary between two extreme limits, especially in the case of the oxide. Thorium oxide, thickness of layer 0.25 mm, intensity of the current 2.2 × 10^11 ampere. Thorium oxide, thickness of layer 0.5 mm, intensity of current 2.5 × 10^11 ampere. Thorium oxide, thickness of layer 2.5 mm, intensity of current 4.7 × 10^11 ampere. Thorium oxide, thickness of layer 3 mm, intensity of current 5.5 × 10^11 ampere. Mean value. Thorium oxide, thickness of layer 6 mm, intensity of current 5.5 × 10^11 ampere. Mean value. Thorium sulfate, thickness of layer 0.25 mm, intensity of current 0.8 × 10^11 ampere. Mean value. There is here some cause of irregularities which do not exist in the case of the uranium compounds. The figures obtained for a layer of oxide 6 mm thick varied between 3.7 and 7.3. The experiments that I made on the absorption of uranium and thorium rays showed that those of thorium are more penetrating than those of uranium, and that the rays emitted by the oxide of thorium in a thick layer are more penetrating than those emitted by a thin layer of the same. The following figures give the fraction of the radiation transmitted by a sheet of aluminium 0.01 thick. Uranium 0.8 fraction of radiation transmitted by the sheet. Uranium oxide U2O5 0.20 fraction of radiation transmitted by the sheet. Uranate of ammonium 0.20 fraction of radiation transmitted by the sheet. Phosphate of uranium and copper 0.21 fraction of radiation transmitted by the sheet. Thorium oxide of thickness 0.25 mm 0.38 fraction of radiation transmitted by the sheet. Thorium oxide of thickness 0.5 mm 0.47 fraction of radiation transmitted by the sheet. Thorium oxide of thickness 3 mm 0.70 fraction of radiation transmitted by the sheet. Thorium oxide of thickness 6 mm 0.70 fraction of radiation transmitted by the sheet. Thorium sulfate of thickness 0.25 mm 0.38 fraction of radiation transmitted by the sheet. With the uranium compounds, the absorption is the same whatever be the compound used, which leads to the conclusion that the rays emitted by the different compounds are of the same nature. The characteristics of the thorium radiation have formed the subject of very complete publications. Mr. Owens has demonstrated that a uniform current is only obtained after some time has elapsed with an enclosed apparatus, and that the intensity of the current is greatly reduced under the influence of a current of air, which does not occur with the compounds of uranium. Mr. Rutherford has made similar experiments, and has explained them by the proposition that thorium and its compounds produce, besides the Becquerel rays, another emanation, composed of extremely minute particles, which remain radioactive for some time after their emission, and are capable of being swept along by a current of air. The characteristics of the thorium radiation, which have reference to the thickness of the layer employed and to the action of air currents, have an intimate connection with the phenomenon of the radioactivity induced and of its propagation from place to place. This phenomenon was observed for the first time with radium, and will be described later. The radioactivity of thorium and uranium compounds appears as an atomic property. M. Becquerel has already observed that all uranium compounds are active, and had concluded that their activity was due to the presence of the element uranium. He also demonstrated that uranium was more active than its salts. I have investigated from this point of view the compounds of thorium and uranium, and have taken a great many measurements of their activity under different conditions. The result of all these determinations shows the radioactivity of these substances to be decidedly an atomic property. It seems to depend upon the presence of atoms of the two elements in question, and is not influenced by any change of physical state or chemical decomposition. The chemical combinations and mixtures containing uranium or thorium are active in proportion to the amount of the metal contained, all inactive material acting as inert bodies and absorbing the radiation. Is atomic radioactivity a general phenomenon? As I have said above, I made experiments to discover whether substances other than compounds of uranium and thorium were radioactive. I undertook this research with the idea that it was scarcely probable that radioactivity, considered as an atomic property, should belong to a certain kind of matter to the exclusion of all other. The determinations I made permit me to say that, for chemical elements actually considered as such, including the rarest and most hypothetical, the compounds I investigated were always at least 100 times less active in my apparatus than metallic uranium. The following is a summary of the substances experimented upon, either as the element or in combination. 1. All the metals or non-metals easily procurable, and some, more rare, pure products obtained from the collection of M. Etard at the École de Physique et de Chimie Industrielle de la Ville de Paris. 2. The following rare bodies: gallium, germanium, neodymium, praseodymium, niobium, scandium, gadolinium, erbium, samarium, and rubidium, specimens lent by M. de Marseille; yttrium, ytterbium, lent by M. Urbain. 3. A large number of rocks and minerals. Within the limits of sensitiveness of any apparatus, I found no simple substance other than uranium and thorium possessing atomic radioactivity. It will be suitable to add a few words here concerning phosphorus. White moist phosphorus, placed between the plates of the condenser, causes the air between the plates to conduct. However, I do not consider this body radioactive in the same manner as thorium and uranium. For, under these conditions, phosphorus becomes oxidized and emits luminous rays, whilst uranium and thorium compounds are radioactive without showing any chemical change which can be detected by any known means. Further, phosphorus is not active in the red variety, nor in a state of combination. In a recent work, M. Bloch has demonstrated that phosphorus undergoing oxidation in air gives rise to slightly motile ions, which make the air conduct and cause condensation of aqueous vapor. Uranium and thorium are elements which possess the highest atomic weights, 240 and 232. They occur frequently in the same minerals. Radioactive minerals. I have examined many minerals in my apparatus. Certain of them gave evidence of radioactivity, for example, pitchblende, thorite, orangite, fergusonite, clevite, chalcolite, autunite, monazite, etc. The following is a table giving in ampere the intensity, I, of the current obtained with metallic uranium and with different minerals. Uranium. Intensity of the current 2.3 × 10⁻11 ampere. Pitchblende from Johann Georgenstadt. Intensity of the current 8.3 × 10⁻11 ampere. Pitchblende from Joachimsthal. Intensity of the current 7.0 × 10⁻11 ampere. Pitchblende from Psibran. Intensity of the current 6.5 × 10⁻11 ampere. Pitchblende from Cornwallis. Intensity of the current 1.6 × 10⁻11 ampere. Clevite. Intensity of the current 1.4 × 10⁻11 ampere. Chalcolite. Intensity of the current 5.2 × 10⁻11 ampere. Autunite. Intensity of the current 2.7 × 10⁻11 ampere. Various thorites. Intensity of the current 0.1, 0.3, 0.7, 1.3, 1.4 × 10⁻11 ampere. Orangite. Intensity of the current 2.0 × 10⁻11 ampere. Monazite. Intensity of the current 0.5 × 10⁻11 ampere. Xenotime. Intensity of the current 0.03 × 10⁻11 ampere. Eschenite. Intensity of the current 0.7 × 10⁻11 ampere. Fergusonite. 2 samples. Intensity of the current 0.4, 0.1 × 10⁻11 ampere. Samarskite. Intensity of the current 1.1 × 10⁻11 ampere. Niobite. 2 samples. Intensity of the current 0.1, 0.3 × 10⁻11 ampere. Tantalite. Intensity of the current 0.02 × 10⁻11 ampere. Carnotite. Intensity of the current 6.2 × 10⁻11 ampere. The current obtained with orangite, native oxide of thorium, varied greatly with the thickness of the layer. By increasing this thickness from 0.25 mm to 6 mm, the current increased from 1.8 to 2.3. All the minerals which showed radioactivity contained uranium or thorium. Their activity is therefore not surprising, but the intensity of the action in certain cases is unexpected. Thus pitchblendes, ores of uranium oxide, are found which are 4 times as active as metallic uranium. Chalcolite, double phosphate of copper and uranium, is twice as active as uranium. Autunite, phosphate of uranium and calcium, is as active as uranium. These facts do not accord with previous conclusions, according to which no mineral should be so active as thorium or uranium. To throw light on this point, I prepared artificial chalcolite by the process of Debray, starting with the pure products. The process consists in mixing a solution of uranium nitrate with a solution of copper phosphate in phosphoric acid and warming to 50° or 60°. After some time, crystals of chalcolite appear in the liquid. Chalcolite thus obtained possesses a perfectly normal activity given by its composition. It is 2½ times less active than uranium. It therefore appeared probable that if pitchblende, chalcolite, and autunite possess so great a degree of activity, these substances contain a small quantity of a strongly radioactive body, differing from uranium and thorium and the simple bodies actually known. I thought that if this were indeed the case, I might hope to extract this substance from the ore by the ordinary methods of chemical analysis. End of section 2. Radioactive Substances. This LibriVox recording is in the public domain. Read by Availle in August 2010. Radioactive Substances by Marie Curie. Chapter 2. Method of Research. Part 1. The results of the investigation of radioactive minerals announced in the preceding chapter led M. Curie and myself to endeavor to extract a new radioactive body from pitchblende. Our method of procedure could only be based on radioactivity, as we know of no other property of the hypothetical substance. The following is the method pursued for a research based on radioactivity. The radioactivity of a compound is determined and the chemical decomposition of this compound is effected. The radioactivity of all the products obtained is determined, having regard to the proportion in which the radioactive substance is distributed among them. In this way, an indication is obtained which may to a certain extent be compared to that which spectrum analysis furnishes. In order to obtain comparable figures, the activity of the substances must be determined in the solid form well dried. Polonium, radium, actinium. The analysis of pitchblende with the help of the method just explained led us to the discovery in this mineral of two strongly radioactive substances chemically dissimilar: polonium, discovered by ourselves, and radium, which we discovered in conjunction with M. Beaumont. Polonium, from the analytical point of view, is analogous to bismuth, and separates out with the latter. By one of the following methods of fractionating, bismuth products are obtained increasingly rich in polonium. 1. Sublimation of the sulphides in vacuo. The active sulphide is much more volatile than bismuth sulphide. 2. Precipitation of solutions of the nitrate by water. The precipitate of the basic nitrate is much more active than the salt which remains in solution. 3. Precipitation by sulphuretted hydrogen of a hydrochloric acid solution, strongly acid. The precipitated sulphides are considerably more active than the salt which remains in solution. Radium is a substance which accompanies the barium obtained from pitchblende. It resembles barium in its reactions, and is separated from it by difference of solubility of the chlorides in water, in dilute alcohol, or in water acidified with hydrochloric acid. We effect the separation of the chlorides of barium and radium by subjecting the mixture to fractional crystallization, radium chloride being less soluble than that of barium. A third strongly radioactive body has been identified in pitchblende by M. Debierne, who gave it the name of actinium. Actinium accompanies certain members of the iron group contained in pitchblende. It appears in particular allied to thorium, from which it has not yet been found possible to separate it. The extraction of actinium from pitchblende is a very difficult operation, the separations being as a rule incomplete. All three of the new radioactive bodies occur in quite infinitesimal amount in pitchblende. In order to obtain them in a more concentrated condition, we were obliged to treat several tons of residue of the ore of uranium. The rough treatment was carried out in the factory, and this was followed by processes of purification and concentration. We thus succeeded in extracting from thousands of kilograms of crude material a few decigrams of products which were exceedingly active as compared with the ore from which they were obtained. It is obvious that this process is long, arduous, and costly. Other new radioactive bodies have been notified since the termination of our work. M. Giesel on the one hand, and Messrs. Hoffmann and Strauss on the other, have announced the probable existence of a radioactive body similar to lead in its chemical properties. At present only a few samples of this substance have been obtained. Radium is, so far, the only member of the new radioactive substances that has been isolated as the pure salt. Spectrum of radium. It was of the first importance to check by all possible means the hypothesis underlying this work of new radioactive elements. In the case of radium, spectrum analysis was the means of confirming this hypothesis. M. de Marseille undertook the examination of the new radioactive bodies by the searching methods which he employs in the study of photographic spark spectra. The assistance of so competent a scientist was of the greatest value to us, and we are deeply grateful to him for having consented to take up this work. The results of the spectrum analysis brought conviction to us when we were still in doubt as to the interpretation of the results of our research. The first specimens of fairly active barium chloride containing radium, examined by M. de Marseille, exhibited together with the barium lines a new line of considerable intensity and of wavelength lambda 381.47 micromicrons in the ultraviolet. With the more active products prepared subsequently, de Marseille saw the line 381.47 micromicrons more distinctly. At the same time other new lines appeared, and the intensity of the new lines was comparable with that of the barium lines. A further concentration furnished a product for which the new spectrum predominated, and the three strongest barium lines, alone visible, merely indicated the presence of this metal as an impurity. This product may be looked upon as nearly pure radium chloride. Finally, by further purification, I obtained an exceedingly pure chloride, in the spectrum of which the two chief barium lines were scarcely visible. The following is a list, according to de Marseille, of the principal radium lines for the portion of the spectrum included between lambda equals 500 and lambda equals 350 micromicrons. The intensity of each line is represented by a figure, the strongest being marked 16. Lambda 482.63, intensity 10. Lambda 472.69, intensity 5. Lambda 469.98, intensity 3. Lambda 469.21, intensity 7. Lambda 468.30, intensity 14. Lambda 464.19, intensity 4. Lambda 460.03, intensity 3. Lambda 453.35, intensity 9. lambda 443.61, intensity 8, lambda 434.06, intensity 12, lambda 381.47, intensity 16, lambda 364.96, intensity 12. All the lines are clear and narrow. The three lines 381.47, 468.30, 434.06 are strong and equal the most intense of those actually known. Two well-marked misty bands are also visible in the spectrum. The first, which is symmetrical, extends from 463.10 to 462.19, with a maximum at 462.75. The second, which is stronger, fades towards the ultraviolet. It begins, sharply defined, at 446.37 and passes through a maximum at 445.52. The region of the maximum extends as far as 445.34, then a nebulous band, gradually fading, extends about as far as 439. In the least refrangible part, not photographed in the spark spectrum, the only significant line is 566.5, approximately, much more feeble, however, than 482.63. The general aspect of the spectrum is that of the metals of the alkaline earths. These metals are known to have well-marked line spectra with certain nebulous bands. According to de Marseille, the position of radium may be among the bodies possessing the most sensitive spectrum reaction. I also have concluded from the work of concentration that in the first specimen examined, which showed clearly the line 381.47, the proportion of radium must have been very small, perhaps about 0.02%. Nevertheless, an activity 50 times as great as that of metallic uranium is required in order to distinguish clearly the principal radium line in the spectra photographed. With a sensitive electrometer, the radioactivity of a substance only 1/100th of that of metallic uranium can be detected. It is clear that, in order to detect the presence of radium, the property of radioactivity is several thousand times more sensitive than the spectrum reaction. Bismuth containing polonium and thorium containing actinium, both very active, examined by de Marseille, have so far each only yielded bismuth and thorium lines. In a recent publication, M. Giesel, who is occupied in preparing radium, states that radium bromide gives a carmine flame coloration. The flame spectrum of radium contains two beautiful red bands, one line in the blue-green and two faint lines in the violet. Extraction of the new radioactive substances. The first stage of the operation consists in extracting barium with radium from the ores of uranium, also bismuth with polonium and the rare earths containing actinium from the same. These three primary products having been obtained, the next step is in each case to endeavor to isolate the new radioactive body. This second part of the treatment consists of a process of fractionation. The difficulty of finding a very perfect means of separating closely allied elements is well known. Methods of fractionation are therefore quite suitable. Besides this, when a mere trace of one element is mixed with another element, no method of complete separation could be applied to the mixture, even allowing that such a method was known. In fact, one would run the risk of losing the trace of the material to be separated. The particular object of my work has been the isolation of radium and polonium. After working for several years, I have so far only succeeded in obtaining the former. Pitchblende is an expensive ore, and we have given up the treatment of it in large quantities. In Europe, the extraction of this ore is carried out in the mine of Joachimsthal, in Bohemia. The crushed ore is roasted with carbonate of soda, and the resulting material washed, first with warm water and then with dilute sulphuric acid. The solution contains the uranium, which gives pitchblende its value. The insoluble residue is rejected. This residue contains radioactive substances. Its activity is 4.5 times that of metallic uranium. The Austrian government, to whom the mine belongs, presented us with a ton of this residue for our research, and authorized the mine to give us several tons more of the material. It was not very easy to apply the methods of the laboratory to the preliminary treatment of the residue in the factory. M. de Bierne investigated this question and organized the treatment in the factory. The most important point of his method is the conversion of the sulphates into carbonate by boiling the material with a concentrated solution of sodium carbonate. This method avoids the necessity of fusing with sodium carbonate. The residue chiefly contains the sulphates of lead and calcium, silica, alumina, and iron oxide. In addition, nearly all the metals are found in greater or smaller amount: copper, bismuth, zinc, cobalt, manganese, nickel, vanadium, antimony, thallium, rare earths, niobium, tantalum, arsenic, barium, etc. Radium is found in this mixture as sulphate, and is the least soluble sulphate in it. In order to dissolve it, it is necessary to remove the sulphuric acid as far as possible. To do this, the residue is first treated with a boiling concentrated soda solution. The sulphuric acid combined with the lead, aluminium, and calcium passes for the most part into solution as sulphate of sodium, which is removed by repeatedly washing with water. The alkaline solution removes at the same time lead, silicon, and aluminium. The insoluble portion is attacked by ordinary hydrochloric acid. This operation completely disintegrates the material and dissolves most of it. Polonium and actinium may be obtained from this solution. The former is precipitated by sulphuretted hydrogen. The latter is found in the hydrates precipitated by ammonia in the solutions separated from the sulphides and oxidized. Radium remains in the insoluble portion. This portion is washed with water, and then treated with a boiling concentrated solution of carbonate of soda. This operation completes the transformation of the sulphates of barium and radium into carbonates. The material is then thoroughly washed with water, and then treated with dilute hydrochloric acid, quite free from sulphuric acid. The solution contains radium as well as polonium and actinium. It is filtered and precipitated with sulphuric acid. In this way, the crude sulphates of barium containing radium and calcium, of lead and of iron, and of a trace of actinium are obtained. The solution still contains a little actinium and polonium, which may be separated out as in the case of the first hydrochloric acid solution. From 1 ton of residue, 10 to 20 kilograms of crude sulphates are obtained, the activity of which is from 30 to 60 times as great as that of metallic uranium. They must now be purified. For this purpose they are boiled with sodium carbonate and transformed into the chlorides. The solution is treated with sulphuretted hydrogen, which gives a small quantity of active sulphides containing polonium. The solution is filtered, oxidized by means of chlorine, and precipitated with pure ammonia. The precipitated hydrates and oxides are very active, and the activity is due to actinium. The filtered solution is precipitated with sodium carbonate. The precipitated carbonates of the alkaline earths are washed and converted into chlorides. These chlorides are evaporated to dryness and washed with pure concentrated hydrochloric acid. Calcium chloride dissolves almost entirely, whilst the chloride of barium and radium remains insoluble. Thus, from 1 ton of the original material, about 8 kilograms of barium and radium chloride are obtained, of which the activity is about 60 times that of metallic uranium. The chloride is now ready for fractionation. Polonium. As I said above, by passing sulphuretted hydrogen through the various hydrochloric acid solutions obtained during the course of the process, active sulphides are precipitated, of which the activity is due to polonium. These sulphides chiefly contain bismuth, a little copper, and lead. The latter metal occurs in relatively small amount, because it has been to a great extent removed by the soda solution, and because its chloride is only slightly soluble. Antimony and arsenic are found among the oxides only in the minutest quantity, their oxides having been dissolved by the soda. In order to obtain the very active sulphides, the following process was employed. The solutions made strongly acid with hydrochloric acid were precipitated with sulphuretted hydrogen. The sulphides thus precipitated are very active and are employed for the preparation of polonium. There remain in the solution substances not completely precipitated in presence of excess of hydrochloric acid, bismuth, lead, antimony. To complete the precipitation, the solution is diluted with water and treated again with sulphuretted hydrogen, which gives a second precipitate of sulphides, much less active than the first, and which have generally been rejected. For the further purification of the sulphides, they are washed with ammonium sulphide, which removes the last remaining traces of antimony and arsenic. They are then washed with water and ammonium nitrate, and treated with dilute nitric acid. Complete solution never occurs. There is always an insoluble residue, more or less considerable, which can be treated afresh if it is judged expedient. The solution is reduced to a small volume and precipitated either by ammonia or by excess of water. In both cases the lead and the copper remain in solution. In the second case a little bismuth, scarcely active at all, remains also in solution. The precipitate of oxides or basic nitrates is subjected to fractionation in the following manner. The precipitate is dissolved in nitric acid, and water is added to the solution until a sufficient quantity of precipitate is formed. It must be borne in mind that sometimes the precipitate does not at once appear. The precipitate is separated from the supernatant liquid and redissolved in nitric acid, after which both the liquids thus obtained are reprecipitated with water and treated as before. The different fractions are combined according to their activity, and concentration is carried out as far as possible. In this way is obtained a very small quantity of a substance of which the activity is very high, but which, nevertheless, has so far only shown bismuth lines in the spectroscope. There is unfortunately little chance of obtaining the isolation of polonium by this means. The method of fractionation just described presents many difficulties, and the case is similar with other wet processes of fractionation. Whatever be the method employed, compounds are readily formed which are absolutely insoluble in dilute or concentrated acids. These compounds can only be redissolved by reducing them to the metallic state, for example by fusion with potassium cyanide. Considering the number of operations necessary, this circumstance constitutes an enormous difficulty in the progress of the fractionation. This obstacle is the greater because polonium, once extracted from the pitchblende, diminishes in activity. This diminution of activity is slow, for a specimen of bismuth nitrate containing polonium only lost half its activity in 11 months. No such difficulty occurs with radium. The radioactivity remains throughout an accurate gauge of the concentration. The concentration itself presents no difficulty, and the progress of the work from the start can be constantly checked by spectral analysis. When the phenomena of induced radioactivity, which will be discussed later on, were made known, it seemed obvious that polonium, which only shows the bismuth lines and whose activity diminishes with time, was not a new element, but bismuth made active by the vicinity of radium in the pitchblende. I am not sure that this opinion is correct. In the course of my prolonged work on polonium, I have noted chemical effects which I have never observed either with ordinary bismuth or with bismuth made active by radium. These chemical effects are, in the first place, the extremely ready formation of insoluble compounds, of which I have spoken above, especially basic nitrates, and, in the second place, the color and appearance of the precipitates obtained by adding water to the nitric acid solution of bismuth containing polonium. These precipitates are sometimes white, but more generally of a more or less vivid yellow, verging on red. The absence of lines other than those of bismuth does not necessarily prove that the substance only contains bismuth, because bodies exist whose spectrum reaction is scarcely visible. It would be necessary to prepare a small quantity of bismuth containing polonium in as concentrated a condition as possible, and to examine it chemically, in the first place determining the atomic weight of the metal. It has not yet been possible to carry out this research on account of the difficulties of a chemical nature already mentioned. If polonium were proved to be a new element, it would be no less true that it cannot exist indefinitely in a strongly radioactive condition, at least when extracted from the ore. There are therefore two aspects of the question. First, whether the activity of polonium is entirely induced by the proximity of substances themselves radioactive, in which case polonium would possess the faculty of acquiring atomic activity permanently, a faculty which does not appear to belong to any substance whatever. Second, whether the activity of polonium is an inherent property, which is spontaneously destroyed under certain conditions, and persists under certain other conditions, such as those which exist in the ore. The phenomenon of atomic activity induced by contact is still so little understood that we lack the ground on which to formulate any opinion on the matter. Note: a work has recently appeared on polonium by M. Markwald. He plunges a small rod of pure bismuth into a hydrochloric acid solution of the bismuth extracted from the pitchblende residue. After some time the rod becomes coated with a very active deposit, and the solution now contains only inactive bismuth. M. Markwald also obtains a very active deposit by adding tin chloride to a hydrochloric acid solution of radioactive bismuth. From this he concludes that the active element is allied to tellurium, and gives it the name of radiotellurium. This active substance of M. Markwald seems identical with polonium from its behavior and from the easily absorbed rays it emits. The choice of a new name for this substance is futile in the present state of the question. End of section 3. Radioactive Substances. This LibriVox recording is in the public domain. Read by Availle in August 2010. Radioactive Substances by Marie Curie. Chapter 2, Method of Research. Part 2. Preparation of the pure chloride of radium. The method by which I extracted pure radium chloride from barium chloride containing radium consists in first subjecting the mixture of the chlorides to fractional crystallization in pure water, then in water to which hydrochloric acid has been added. The difference in solubility of the two chlorides is thus made use of, that of radium being less soluble than that of barium. At the beginning of the fractionation, pure distilled water is used. The chloride is dissolved and the solution raised to boiling point and allowed to crystallize by cooling in a covered capsule. Beautiful crystals form at the bottom, and the supernatant, saturated solution is easily decanted. If part of this solution be evaporated to dryness, the chloride obtained is found to be about 5 times less active than that which has crystallized out. The chloride is thus divided into 2 portions, A and B, portion A being more active than portion B. The operation is now repeated with each of the chlorides A and B, and in each case 2 new portions are obtained. When the crystallization is finished, the less active fraction of chloride A is added to the more active fraction of chloride B, these two having approximately the same activity. Thus there are now 3 portions to undergo afresh the same treatment. The number of portions is not allowed to increase indefinitely. The activity of the most soluble portion diminishes as the number increases. When its activity becomes inconsiderable, it is withdrawn from the fractionation. When the desired number of fractions has been obtained, fractionation of the least soluble portion is stopped, the richest in radium, and it is withdrawn from the remainder. A fixed number of fractions is used in the process. After each series of operations, the saturated solution arising from one fraction is added to the crystals arising from the following fraction. But if after one of the series the most soluble fraction has been withdrawn, then after the following series a new fraction is made from the most soluble portion, and the crystals of the most active portion are withdrawn. By the successive alteration of these 2 processes, an extremely regular system of fractionation is obtained, in which the number of fractions and the activity of each remains constant, each being about 5 times as active as the subsequent one, and in which, on the one hand, an almost inactive product is removed, whilst, on the other, is obtained a chloride rich in radium. The amount of material contained in these fractions gradually diminishes, becoming less as the activity increases. At first 6 fractions were used, and the activity of the chloride obtained at the end was only 0.1 that of uranium. When most of the inactive matter has been removed and the fractions have become small, 1 fraction is removed from the one end, and another is added to the other end, consisting of the active chloride previously removed. A chloride richer in radium than the preceding is thus obtained. This system is continued until the crystals obtained are pure radium chloride. If the fractionation has been thoroughly carried out, scarcely any trace of the intermediate products remain. At an advanced stage of the fractionation, when the quantity of material in each fraction is small, the separation by crystallization is less efficacious, the cooling being too rapid and the volume of the solution to be decanted too small. It is then advisable to add water containing a known quantity of hydrochloric acid. This quantity may be increased as the fractionation proceeds. The advantage gained thus consists in increasing the quantity of the solution, the solubility of the chlorides being less in water acidified with hydrochloric acid than in pure water. By using water containing much acid, excellent separations are effected, and it is only necessary to work with 3 or 4 fractions. The crystals, which form in very acid solution, are elongated needles, those of barium chloride having exactly the same appearance as those of radium chloride. Both show double refraction. Crystals of barium chloride containing radium are colorless, but when the proportion of radium becomes greater, they have a yellow coloration after some hours, verging on orange, and sometimes a beautiful pink. This color disappears in solution. Crystals of pure radium chloride are not colored, so that the coloration appears to be due to the mixture of radium and barium. The maximum coloration is obtained for a certain degree of radium present, and this fact serves to check the progress of the fractionation. I have sometimes noticed the formation of a deposit composed of crystals of which one part remained uncolored whilst the other was colored, and it seems possible that the colorless crystals might be sorted out. The fractional precipitation of an aqueous solution of barium chloride by alcohol also leads to the isolation of radium chloride, which is the first to precipitate. This method, which I first employed, was finally abandoned for the one just described, which proceeds with more regularity. I have, however, occasionally made use of precipitation by alcohol to purify radium chloride, which contains traces of barium chloride. The latter remains in the slightly aqueous alcoholic solution and can thus be removed. M. Giesel, who, since the publication of our first researches, has been preparing radioactive bodies, recommends the separation of barium and radium by fractional crystallization in water from a mixture of the bromides. I can testify that this method is advantageous, especially in the first stages of the fractionation. Determination of the atomic weight of radium. In the course of my work I determined at intervals the atomic weight of the metal contained in specimens of barium chloride containing radium. With each newly obtained product I carried the concentration as far as possible, so as to have from 0.1 grams to 0.5 grams of material containing most of the activity of the mixture. From this small quantity I precipitated with alcohol or with hydrochloric acid some milligrams of chloride for spectral analysis. Thanks to his excellent method, de Marseille only required this small quantity of material to obtain the photograph of the spark spectrum. I made an atomic weight determination with the product remaining. I employed the classic method of weighing as silver chloride the chlorine contained in a known weight of the anhydrous chloride. As control experiment, I determined the atomic weight of barium by the same method, under the same conditions, and with the same quantity of material, first 0.5 grams and then 0.1 grams. The figures obtained were always between 137 and 138. I thus saw that the method gives satisfactory results, even with a very small quantity of material. The first two determinations were made with chlorides, of which one was 230 times and the other 600 times as active as uranium. These two experiments gave the same figure as the experiment with the pure barium chloride. There was therefore no hope of finding a difference, except by using a much more active product. The following experiment was made with a chloride, the activity of which was about 3,500 times as great as that of uranium, and this experiment enabled me for the first time to observe a small but distinct difference. I found, as the mean atomic weight of the metal contained in this chloride, the number 140, which showed that the atomic weight of radium must be higher than that of barium. By using more and more active products and obtaining spectra of radium of increasing intensity, I found that the figures obtained rose in proportion, as is seen in the following table. The figures of column A must only be looked upon as a rough estimate. The calculation of the activity of strongly radioactive bodies is difficult, for many reasons which will be discussed later. Activity, 3500. Atomic weight found 140. Spectrum of radium faint. Activity 4700. Atomic weight found 141. Activity 7500. Atomic weight found 145.8. Spectrum of radium strong, but that of barium predominating. Activity order of magnitude 10 to the power of 6. Atomic weight found 173.8. The two spectra of almost equal intensity. Activity order of magnitude 10 to the power of 6. Atomic weight found 225. Only a trace of barium present. A represents the activity of the chloride, that of uranium being unity, M the atomic weight found. At the termination of the processes described above, I obtained, in March 1902, 0.12 grams of radium chloride, of which de Marseille made the spectral analysis. This radium chloride, in the opinion of de Marseille, was fairly pure. Its spectrum, however, showed the three principal barium lines with considerable intensity. I made 4 successive estimations of the chloride, the results of which are as follows. 1. Anhydrous radium chloride 0.1150. Silver chloride 0.1130. Atomic weight found 220.7. 2. Anhydrous radium chloride 0.1140. Silver chloride 0.1119. Atomic weight found 223.0. 3. Anhydrous radium chloride 0.11135. Silver chloride 0.1086. Atomic weight found 222.8. 4. Anhydrous radium chloride 0.10925. Silver chloride 0.10645. Atomic weight found 223.1. I then repurified this chloride and obtained a much purer substance, in the spectrum of which the two strongest barium lines were very faint. Given the sensitiveness of the spectrum reaction of barium, de Marseille estimated that the purified chloride contained only the merest traces of barium, incapable of influencing the atomic weight to an appreciable extent. I made 3 determinations with this perfectly pure radium chloride. The results were as follows. 1. Anhydrous radium chloride 0.09192. Silver chloride 0.08890. Atomic weight found 225.3. 2. Anhydrous radium chloride 0.08936. Silver chloride 0.08627. Atomic weight found 225.8. 3. Anhydrous radium chloride 0.08839. Silver chloride 0.08589. Atomic weight found 224.0. The mean of these numbers is 225. They were calculated in the same way as the preceding ones, by considering radium as a bivalent element, the chloride having the formula RaCl2, and taking for silver and chlorine the values silver 107.8, chlorine 35.4. Hence the atomic weight of radium is radium 225. The weighings were made with a Curie aperiodic balance perfectly regulated, accurate to the 20th of a milligram. This direct reading balance permits of very rapid weighing, a condition which is essential in the case of the anhydrous chlorides of radium and barium, which gradually absorb moisture in spite of the presence of desiccating substances in the balance. The bodies to be weighed were placed in a platinum crucible. This crucible had been long in use, and its weight did not vary the 10th part of a milligram during the course of one operation. The hydrated chloride obtained by crystallization was placed in the crucible and heated till converted into the anhydrous chloride. When the chloride has been kept for several hours at 100 degrees, its weight becomes constant and does not change even if the temperature is raised to 200 degrees. The anhydrous chloride thus obtained constitutes, therefore, a perfectly definite body. The following is a series of determinations on this point. The chloride, 100 mg, is dried in the oven at 55 degrees and placed in a desiccator over anhydrous phosphoric acid. It then gradually loses weight, which proves that it still contains moisture. In the course of 12 hours the loss was 3 mg. The chloride is replaced in the stove and the temperature raised to 100 degrees. During this process the chloride lost 6.3 mg in weight. After being left 3 hours 15 minutes in the oven, it lost 2.5 mg more. The temperature was maintained for 45 minutes between 100 and 120 degrees, which caused a loss of weight of 0.1 mg. Then, after being kept for 30 minutes at 125 degrees, the chloride showed no diminution in weight. Then, however, after 30 minutes at 150 degrees, it lost 0.1 mg. Finally, after being heated for 4 hours at 200 degrees, it lost 0.15 mg. During these operations, the crucible varied from 0.05 mg. After each determination of the atomic weight, the radium was converted into the chloride in the following manner. To the solution containing the weight radium nitrate and excess of silver nitrate was added pure hydrochloric acid. The silver chloride was filtered off. The solution was evaporated to dryness several times with excess of pure hydrochloric acid. In this way, the nitric acid is entirely removed. The precipitated silver chloride was always radioactive and phosphorescent. In determining the amount of silver contained in it, I satisfied myself that no ponderable amount of radium had been carried down with it out of the solution. The method I pursued was to reduce the silver chloride, precipitated in the crucible by hydrogen, generated from dilute hydrochloric acid and zinc. After washing, the crucible was weighed with the metallic silver contained in it. I made another experiment which showed that the weight of radium chloride regenerated was the same as that before beginning the operation. These verifications are not so reliable as direct experiments, but they serve to indicate the absence of any significant error. From its chemical properties, radium is an element of the group of alkaline earths, being the member next above barium. From its atomic weight also, radium takes its place in Mendeleev's table after barium with the alkaline earth metals, in the row which already contains uranium and thorium. Characteristics of the radium salts. The salts of radium, chloride, nitrate, carbonate, and sulfate, resemble those of barium when freshly prepared, but they gradually become colored. All the radium salts are luminous in the dark. In their chemical properties, the salts of radium are absolutely analogous to the corresponding salts of barium. However, radium chloride is less soluble than barium chloride. The solubility of the nitrates in water is approximately the same. The salts of radium are the source of a spontaneous and continuous evolution of heat. Fractionation of ordinary barium chloride. We have endeavoured to determine whether commercial barium chloride contains small quantities of radium chloride which escape detection with the means of estimation at our command. For this purpose we fractionated a great quantity of commercial barium chloride in the hope of thus concentrating the trace of radium chloride if such were present. 50 kilograms of commercial barium chloride were dissolved in water. The solution was precipitated by hydrochloric acid free from sulphuric acid, which yielded 20 kilograms of the precipitated chloride. This was dissolved in water and partially precipitated by hydrochloric acid, which gave 8.5 kilograms of precipitated chloride. This chloride was fractionated by the method used for the barium chloride containing radium, and at the end of the process 10 grams of chloride were obtained, corresponding to the least soluble part. This chloride showed no radioactivity. It therefore contained no radium. This substance is, consequently, absent from the ores of barium. End of section 4.